Hello, my name is Matt Aultman. I'm a PhD candidate from Ohio State, and for my flow visualization, I'll be presenting the limitations of particle number density on measurements of Reynolds stresses in a hypersonic turbulent boundary layer using PIV. PIV and other particle tracking methods attempt to measure the velocity field by measuring the velocity of the tracer particle field. However, for high-speed flows, such as a supersonic isolator shown here, the particle velocity can deviate from the actual flow velocity. For fluctuating base quantities like the Reynolds stresses, parameters such as particle mass via the Stokes number can cause large deviations from the true flow field. The high-speed flow of interest for this visualization is a direct numerical simulation of a Mach 4.9 turbulent boundary layer subjected to 3 pressure gradients: a 0 pressure gradient flat plate case, a favorable weak pressure gradient, and a favorable strong pressure gradient. Looking at the Reynolds stresses, we see that the streamwise component matches well between the DNS and the experiments. The shear component compares well, although small deviations have developed. These deviations are likely due to the wall normal fluctuations, which show a great deal of deviation between the DNS and experimental PIV. So we want to figure out why there's such a large deviation by testing a synthetic PIV on our DNS data. The way PIV typically works is you have a flow field. This flow field is then seeded with particles, and a snapshot is taken at a time t1. Then, the particles propagate with time, and another snapshot is taken at time t2. These images are taken with digital cameras, which discretize the field of view. Taking a single pixel, the pixel size can be calibrated to calculate its physical size in both x and in y. By using cross correlations between the two snapshots, a correlation peak can be calculated to determine the displacement of a group of particles. Knowing the time between the two snapshots, along with the displacement, the velocity can be calculated from the particle field. Thus, for synthetic PIV, we need 2 components: a velocity field and particles propagated throughout to generate PIV images. For our flow field, we consider the Mach 4.9 turbulent boundary layer from before. We take a slice and consider only the 2D field. We then limit ourselves to the region corresponding to the previous experimental measurements. This gives us our flow field, which we subjected to Lagrangian particle tracking. With our particles propagated throughout the flow field, we use a Gaussian distribution to illuminate our particles. These illuminated regions are then discretized on a grid similar to the pixels of a digital camera and are converted to images. Now we can generate synthetic particle images for PIV. In our previous work at SciTech, we found that the PIV velocity field to be highly sensitive to spatial resolution. Decreased resolution of PIV results in dampening of the fine-scale turbulent fluctuations as demonstrated by the filtered DNS on the right. When increasing the resolution by decreasing the PIV window size, we found that there was a point in which the correlation peaks were inaccurately calculated, leading to non-physical fluctuations as seen on the right. We speculated that this was caused by a reduction in the number of particles for the smaller windows. To test this, we varied the number of particles via particles per millimeter squared, or ppmm. As can be seen, the high-density fields are easily to visualize the turbulent structures. However, moderate particle densities are still good enough to capture the correlation peaks, while sparse particle densities can cause issues. Looking at the Reynolds stresses, the streamwise component shows little deviation from the raw DNS, even at the lowest particle density. The shear component shows a similar trend for the strong pressure gradient case on the bottom, but at the lowest particle density, the 0 pressure gradient case shows substantial deviations. This carries over for both in the wall normal component, and we see that deviations begin to develop at 20 and 10 particles per millimeter squared for the 0 and strong pressure gradient cases respectively. By normalizing these values by particles per window, or ppw, we see that this deviation begins at roughly 10 particles per window, indicating that for the current conditions, 10 particles are needed per window to effectively resolve the fluctuating velocity field to capture the Reynolds stresses. Therefore, we can use this criteria in future studies to further test the effects of spatial resolution on PIV measurements. Thank you for your time.